All right, thank you for the introduction. Sorry, can you hear me? Yes? Okay, cool. Hi everyone, my name is Kevin Louie. I've been an engineer at Meta for the past 7 years, and I'm really excited today to be able to talk a little bit about how end-to-end encrypted backups work at WhatsApp, which is a feature that we launched for our users towards the end of 2021 and mostly throughout 2022. So for this talk, I'm going to start with a little bit of motivation behind what we mean by end-to-end encrypted backups, why they're important, and then we'll get into the details of how the protocol actually works. Okay, so just as a review, in any end-to-end encrypted messaging app, there's this security guarantee that essentially states that any two users should be able to establish a secure communication channel between them with the guarantee that no one except for the endpoints, the sender and receiver, should be able to read these messages. And a popular feature that many people enable on their end-to-end encrypted messaging apps is something called automatic cloud backups. And the idea behind this is that essentially like a plain text copy of your messages are periodically synced and uploaded to a cloud storage provider, so that if the user ends up losing their device and wants to access the messages on the lost device, then they can recover them by getting a new device and then authenticating with the cloud storage provider to get their messages again. And the problem with this cloud backup situation is that it kind of weakens the ideal security promise of end-to-end encryption, right? Because now, in addition to Alice and Bob who have access to the messages, there's this cloud storage provider who also has access to the plain text of these messages. And this is not just a theoretical weakness. This is, in the past, there have been some very high-profile cases where users will enable these automatic cloud backups, thinking that there's still end-to-end encryption protecting their messages, but then say like a government agency comes and goes to the cloud storage provider to get access to the plain text messages, and the user's confused as to how the end-to-end encryption was broken in WhatsApp. So up until 2022, WhatsApp users basically had two options. Either they don't enable backups and risk losing access to their messages if they lose their device, or they enable backups with, say, iCloud or Google Drive, and they have to essentially deal with the consequences of having weaker guarantees around the confidentiality of their messages. So yeah, basically there's this natural tension that exists. Oh, sorry. There's this natural tension that exists between usability and privacy here, right? Ideally, we want users to have the best of both options instead of having to choose usability over privacy or vice versa. So this is what we mean by end-to-end encrypted backups. Essentially, we want to make sure that we can still do backups, but no one except for the endpoints, the users themselves, can access the backup data. And so there are two kind of potential solutions here. One way we can try to achieve this is to essentially have users just like write down a serialized version of their encryption key. So like imagine you have a 256-bit backup key, then we show the 256 bits to you and ask the users to store it somewhere safe, right? And we actually do have this option, but we don't expect that most users will actually do this. So there's another option that we provide, which is to allow users to set a memorable password that will gate access to their backup key, and then enforce a maximum attempt counter on top of that. So the idea is we give the user a certain number of attempts to enter their password to get access to their backup key, and if, say, they fail after 10 attempts, then the backups are actually irrecoverable from that point forward. So this protocol that's behind this password with enforcing attempt limit method will be the subject of today's talk. Okay, so in this protocol, there are three parties. There's going to be the client, there's the cloud provider where the backups are stored using encryption, and then there's a key vault that's managed by WhatsApp, which uses an HSM to store the user's encryption keys. And the way the flow works is first the client will generate an encryption key and register a password to the key vault, at which point their encryption key gets stored in the vault, and the encryption key is then in parallel used to encrypt the messages that get uploaded to the cloud provider. And then when a user wants to recover their backups, they need to submit the same password that was used during registration to retrieve their key, which is then used to, once they have the key, decrypt the encrypted message content that they retrieve from the cloud storage provider. And if they enter an incorrect password, then the user does not get their key back, and this attempt counter goes up by 1. So from a cryptography perspective, the two interesting parts which we'll cover are A, how does the key vault work that WhatsApp maintains? And B, how do clients actually use a password to authenticate to this key vault in a secure manner? Okay, so here's a more detailed view of what's going on inside the WhatsApp key vault. And by the way, before I describe this entire system, I just want to caveat that this is very much inspired by other works at other companies. So for example, Apple in the past has talked about a version of this. Signal has a blog post about their own version of this. And I think Google also has one as well. So this is by no means a new design that we've come up with entirely on our own. Okay, so first off, we use HSMs, which stand for Hardware Security Modules, as the hardware-backed security solution for providing a tamper-resistant execution environment, assuming that you trust the HSM vendor's statements. And the HSMs provide protection for the master secret keys that are used in this vault. And the interesting thing about them is that they can be essentially programmed using a set of admin cards, which will allow us as the engineers to load custom code onto these modules and then run it on the HSMs. And the way that we use these admin cards to initialize the system is with, you can imagine like a trusted ceremony that loads the key vault code onto these HSMs. And then after we load that code, we then physically destroy the admin cards. And the reason for this is that we don't want to be able to have the ability to update the code on these HSMs after the fact. In particular, we wouldn't want to have a secure system and then later on try to insert a backdoor, for instance, by changing the code in the HSM. So what we're really going for here, I guess, is an immutable execution environment with this procedure. Right. And then we use the HSMs to store the encryption keys that the client generates and needs to be able to recover. And we also need these HSMs to be able to store an attempt counter for every user account so that once the maximum attempts for wrong passwords have been reached, then the HSM refuses to ever return that key for any user. Okay, so one challenge that we had to deal with is that HSMs, they only have a very limited amount of secure memory that they can manage, which is going to be way smaller than what's actually needed to store all the encryption keys that correspond, and also the attempt counters for every WhatsApp user, right? Like WhatsApp has billions of users. These HSMs have maybe like megabytes at most of secure memory. So to address this, the HSMs rely on an external storage for these values, where the HSM first encrypts all the blobs of data that it would normally store for a user using a key that only the HSM knows, and then implicitly maintains a Merkle tree of all these data blobs where the root hash of the Merkle tree is kept in the secure memory location in the HSM. And the idea behind this is that now every time the HSM wants to add or update an entry to the database, then it will do so and then ask the database layer, which we consider untrusted, to provide a Merkle inclusion proof that the value was actually updated correctly. And if the proof fails to verify, because the database operator was, say, acting maliciously or trying to do a rollback attack on the values, then the HSM can detect this. And then similarly, when the HSM wants to look up a specific value, like see what the current attempt counter for a user is, then it also asks for an inclusion proof to verify that the database operator essentially isn't playing any tricks on it. Okay, and then additionally, what we have pictured here is not just a single HSM, but a cluster of HSMs, and this is mainly for reliability purposes. If one HSM has a hardware failure, then we want to make sure that the system is still up and running because we threw away our ability to update the code on these HSMs. So what we do is we have this quorum of nodes, each redundantly storing the same data and communicating with each user using secure channels in between the HSMs themselves to establish consensus. And then, yeah, and this is extra important because if we're trying to enforce, say, like a global attempt counter for each account, since we want to make sure that each password attempt, that if a user contacts one HSM and a password attempt fails, then all HSMs know about it. Otherwise, like if we have a cluster of 5 HSMs and we want to, and each enforces a counter of say up to 10, then this would really be like having a total of 50 attempts for each user. Okay, so we've covered the infra setup. Basically, we have this quorum of HSMs. Each are maintaining these Merkle trees for this gigantic database of records for each user containing encryption keys and how many attempts have been used to try to retrieve these encryption keys. Now we're ready to talk about the second piece, which is how does the client actually authenticate itself to the HSM cluster using a password? And that's going to be the main focus for the rest of these slides. Okay, so first, in order for the client to know that it's actually talking to the correct HSM or set of HSM servers, there's going to be a public key that's associated with the HSM that the client verifies. And this public key is distributed to the client on app install. So this kind of serves as the bootstrapping mechanism for the root of trust for authentication here. And there are two options that we considered here. Option one is kind of like the most straightforward option, which is for the client to just say encrypt their password to the HSM's public key so that the HSM can decrypt it, or you can imagine they first hash the password and then the HSM decrypts to get the hash of the password and then check against what was registered. And if it matches, then the client just encrypts their backup key in the same way and the HSM stores it. Right, but one problem with this approach, and by the way, this is what pretty much like, if you imagine logging into any website that requires a username and password, this is probably what they do with the password, like passwords over TLS. And one problem with this approach is that the privacy for the user's password relies entirely on the user trusting the hardware security layer in our setup, because the HSM gets to see like a plain text version of either the password or the hash of the password, depending on how you do that. So in our design, we decided to go for a slightly more advanced approach, which is to use a password authenticated key exchange protocol called OPAKE. And one really cool thing about OPAKE is that it has this guarantee that the password is never actually exposed to the HSM server in plain text. And we'll talk a little bit more about that in just a second. Okay, so OPAKE is a protocol that was presented in Eurocrypt in 2018. And there's actually a long line of works in the PAKE domain that achieve, I guess, like various properties. And in the OPAKE paper, the authors present a stronger notion of security than what was previously achievable, called a strong asymmetric password authenticated key exchange protocol. And just for some background here, in a normal asymmetric PAKE, there is a client and there's a server, and the client has a password, server has, you can say like a one-way function of the password, and together they engage in a protocol that allows them to establish a shared secret using these two starting values. And the new thing at the time with OPAKE was that they introduced this definition of a strong asymmetric PAKE, which is basically a way of saying that the protocol is resistant to a class of attacks called pre-computation attacks. And so a pre-computation attack is this idea that an attacker can essentially, if they want to be able to try to recover the server's hash of the password, they could build like a rainbow table or some sort of pre-computing table before compromising the server, so that once they have this table, and then if they're able to compromise the server, then they can immediately recover passwords. So this is kind of like outside the scope of this talk, but I guess the high level idea is there is the stronger security notion for OPAKEs, and OPAKE achieves it. And also OPAKE was selected as the winner of the asymmetric PAKE competition that was held by the CFRG in 2020. They had two competitions, one for symmetric PAKEs, one for asymmetric, and OPAKE was selected as the protocol to standardize for asymmetric PAKEs, which definitely weighed into our decision for using it within WhatsApp. So anyway, one of the main results of this paper is a practical construction or instantiation of achieving a strong APAKE from two things: an oblivious pseudorandom function and an authenticated key exchange. And in our case, we use something called DHOPRF, which is this function here. It's basically a specific instantiation of an oblivious pseudorandom function. Okay, So there are two flows here. There's backup registration and there's backup recovery. And each flow involves a series of messages that are passed between client and server. Backup registration is triggered when you enable the encrypted backups feature on your phone, and that's when you have to select a password. And backup recovery is triggered when, say, you lose your old phone and you are trying to recover your message history. And here's where you have to enter that same password you used for registration in order to retrieve your messages. Okay, so I'm going to try to go through the protocol. So for registration, the client starts out with a backup key K, a password, and the HSM's public key. And the HSM starts out with its private key. And remember, we assume that the HSM public key has already been distributed to the client on app install, so it's baked into the code. And so in this protocol, we'll be doing operations over a prime order group. And in the first step, the client chooses a random scalar R and sends alpha, which is hash of the password to the R, where this hash function is a hash to curve operation. By the way, if you've seen OPRFs before, this might just be review. And then the server gets alpha. It then picks out a random scalar, let's call it k prime, along with the nonce, and then computes beta, which is just alpha raised to the k prime, and sends this along with the nonce back to the client. And then in step 5, oops, sorry. In step 5, the client takes beta, it raises it to the 1 over r, and then hashes this along with the password. And here we can imagine also using a slow password hashing function like pvkdf to get two outputs, something called an export key and a client private key, which we're going to use in the next step, or sorry, in the recovery flow. And then in step 6, the client has these two outputs. It AES encrypts their actual backup key K using the export key, and then it also computes the public key component for their private key that was derived from this pvkdf operation. And then finally, it uses a CCA secure encryption scheme to encrypt using the HSM's public key the value k star, which is the AES output, along with this entire registration transcript. Okay, and then the server, upon receiving the ciphertext, is going to decrypt, verify the transcript, and then stores k star, k prime, and the client public key for that user. Okay, so definitely a lot of details here, but the takeaway is that the client and server are essentially jointly computing the output of a pseudo-random function, where the input is not exposed to the server and the key is not exposed to the client. And the server generates a random PRF key and ends up storing a k star, which is the encryption of the sensitive payload, which in this case is the client's backup key k, using a key that's derived from the output of the PRF, along with also storing a client public key, where the corresponding private key component is also derived from the output of the PRF, and that's it. Okay, so now for the recovery flow, the client starts with a password and the HSM public key again, and the server has the HSM private key, along with 3 elements of the client record, this k star, k prime, and the client public component. And step 1 is almost the same as in registration, where the client picks a random scalar R, computes alpha, which is hash of password to the R, and this time also the client selects an ephemeral private key for the key exchange component and sends over the public key component of that ephemeral private key. And next, the server picks its own ephemeral private key, uses k prime to construct beta in the same way as in registration, and also has a signature attached to the to beta, which is sent to the client. And critically, at this point, the server also decrements the attempt counter, or sorry, increments the attempt counter for the client, so that the server basically, remember, we're not just doing an authentication protocol with a password, but we also want to make sure that we're keeping track of the number of failed attempts that the client has made. So this is the attempt counter for that interaction. And next, the client is going to recompute the PRF output using the password hashing function in the same way. And here, the guarantee is that if the PIN was the same as what was registered, then the resulting export key and the client private key will be the same. And otherwise, the client gets a completely independent looking output, which should be useless to them. Okay, so assuming that the client did use the same password, then they use the server's static public key, the ephemeral public key, and the client's static key to obtain a shared secret key, and finally sends a message to the server to complete the key exchange. Okay, and then to finish off the protocol, the server verifies that the key exchange is complete, and if successful, resets the attempt counter and also derives the same shared secret key, and finally uses, or it takes K-star and encrypts this using the shared secret key, sending the ciphertext over back to the client. And the very last step, the client takes the ciphertext, decrypts this using the shared secret key, and then also decrypts using the export key to finally retrieve the original backup key K. Okay, so thanks for bearing with me on that. There's a lot of details, but one part that I wanted to highlight in this design is that we're decrementing the attempt counter in step 3, which is kind of like a weird place to do it because it's in the middle of the protocol. It seems like the most logical thing would be to only decrement once the server realizes that the client entered an incorrect password, right? So maybe one like open question is, why do we decrement in step 3 instead of step 8? And the interesting thing, I guess I'm answering the question, but the interesting thing about Opaque is that unlike a normal password authentication protocol where, say, the client just sends a password and the server computes the hash of it, here in Opaque, it's actually the client that first learns whether or not the attempt was successful, right? So the server actually has to rely on the client to tell that the password attempt was unsuccessful before it can change its attempt counter. So if we were to move that decrement attempt counter step to step 8, this would actually be like completely insecure because the client could just check whether or not their password attempt was wrong and then like not tell the server and then try again. And we would have no reliable way to actually track failed attempts. So that's why we actually have to include that in step 3 before the client is able to, or before the server has to wait for the client response. So that's just kind of like one example of a lot of the subtleties that go into this design. And so it's not just a matter of directly applying Opaque, I guess maybe as a future message for other companies or people who want to implement encrypted backups that you have to be really careful with using Opaque. You can't just use Opaque and expect that the attempt counters will just magically work. Yeah. Okay, so that was a high-level overview of the protocol. And in 2021, we also invited NCC Group to audit the design of this protocol, as well as the implementation of it for the entire encrypted backups code base within WhatsApp. And they reported a bunch of findings, which we addressed, and you can find more of them in this public report, which is on their website. We've also released a separate white paper, which covers a lot of the details that I covered today regarding the overall design, maybe with a little bit less detail. And finally, I want to talk a little bit more about what we've been doing with the Opaque protocol externally. So when we were in the design phase of this project, we realized that Opaque was the right solution to this problem, but one major issue was that there weren't really any like off-the-shelf implementations that we could use, which is to be expected because this paper came out in 2018. So we decided to implement Opaque ourselves and open source the implementation so that other people who maybe want to use Opaque for different reasons or do encrypted backups for another application would be able to also do so. And we put a lot of effort into making the API as simple as possible. So right now you can go to crates.io if you're a Rust fan and find the implementation that we're using as is to serve production traffic to WhatsApp users who've enabled encrypted backups. And also that code itself has been audited by NCC where we have a public report just for the Opaque library. Okay, so 2 potential future work directions that I guess I want to call out here. One, which is that we have this like really complicated infra setup, which we try to model after this confidential and immutable execution environment. And one issue with the current design is that it inherently requires users to trust that we did what we said we did, right? Like I can stand here and say that we threw away the keys, but how do you, or that we threw away the admin cards, but how do you actually know that we did that? And so the open question here is, can we implement some setup maybe with like remote attestation or with remote attestation that allows us to give some proofs to the clients that they can actually verify our setup? And the second, which is kind of related to the first, is that the weakness here is the hardware security aspect of things. So can we maybe further mitigate some of those weaknesses by considering like a threshold authentication scheme which splits secrets across multiple machines, so that if we're just talking about a compromise of a single machine, that won't be enough to compromise the entire system. Okay, so last slide. Just want to wrap up. I guess as a summary, we've enabled end-to-end encrypted backups as a feature for WhatsApp users. This feature uses a combination of HSMs plus the OPAC protocol for password-based authentication. And at the end of last year, over 100 million WhatsApp users have enabled end-to-end encrypted backups, which is like a number that surprised me for sure. And right now you can turn this on if you navigate to the chat backup page under encryption settings. It's an available feature for everyone. All right, thank you.
Thank you very much. Are there any questions? Yes, please.
Is the password that you put into OPAC the same as the API login password? And do you use OPAC on the API logins?
By API login password, you mean, so in WhatsApp, you don't have a login. You just authenticate using like your
So the
phone
password
number.
is only for backups?
Yes, yeah.
Okay.
This password is specific to backups.
That was my question. Thank you.
Thank you very much for the interesting talk. The protocol seems to have two different aspects. There's one that uses these cutting edge protocols and standards like OPAC, but there's a certain other part of the protocol that seems to be original. The recovery protocol with the multi-round trip thing. I was wondering what are the constraints that led to certain choices, namely the usage of AES and specifically also the usage of PBKDF. Was it a hardware, usually this stuff is due to a hardware or environment constraint, so I was wondering if you could elaborate on that. Thank you.
Yeah, absolutely. So to clarify, PBKDF is what's done by the clients, not the server. So it's kind of reversed because in OPAC, the clients end up doing a lot of operations, not the server. So unfortunately, we were only able to, I guess, due to client phone, like mobile phone restrictions, we only had access to PBKDF there. It would be nice to have used like Scrypt or something like that, but we didn't have that option. And then I guess, oh, you were also asking about AES there. I guess, yeah, that was also just what was available on the client library because the client is actually the one that has to run the AES protocol. So I don't know if that answered your question, but.
What kind of consensus requirements do you, what kind of consensus requirements do you apply to the rate limiting data? Like how many HSMs could die and have the service still be operable?
Yeah, so we currently, so we have like, say, a quorum of, I don't know the exact number, but say like 5 HSMs in an island, and we want to be able to tolerate like, so that we need at least a majority, so 3 out of 5 being able to still run. When more fail, then we run into issues. I guess it's a short way of saying it.
Interesting.
Thank you very much for the talk. As CFRG chair, we are really glad that you chose OPAC that was the winner of the PEC selection process. And my question is about the following. Do you have any countermeasures against someone just DDoSing someone's backup? So if the attacker just tries wrong passwords for 10 times or more, the backup could become unavailable to anyone. So anyone can just block using their backup. Is it right, or you have some countermeasures against this?
Yeah, so I guess if you mean anyone as in like anyone in the world, you first have to prove that you are the user before you can try to make an attempt towards guessing their password. And there, that just relies on the normal WhatsApp mechanisms for authenticating that you actually have access to this phone, which is SMS. If you're asking about like internal attacks, like can we as WhatsApp engineers try to like to guess 10 attempts for each account, we can. And I guess the main, like the purpose of having that attempt counter is so that mainly we can only have 10 attempts to do that, or if someone coerced us into trying to make these guesses, they would only have 10 attempts to do so. So in this case, we actually chose, I guess, to value the DDoS to be like lower than, like, we'd rather lose the information rather than have some sort of backdoor or some way in which the key or the password could be exposed to us.
Makes sense. Thank you.
There was a question online, Nuri Al-Hawari. Did you have to reassess the formal security proof of OPAC after modifying it for the use case?
Sorry, did we have to?
Did you have to reassess the formal security proof of OPAC after modifying it?
Oh, so actually, yeah. This protocol, as we described it, actually does still use OPAC in a black box manner. We just added a bunch of bells and whistles on top of it. So it didn't actually end up changing anything to do with the OPAC protocol or the security proof for it.
Question?
Thank you. It's a question, I think it's that I got it wrong because I thought you had this counter. I thought it was precisely for rate limiting, but you said it wasn't.
Sorry, yeah, not rate limiting, or I guess if you mean rate limiting as in like trying over a period of time, it's not rate limiting, it's like a attempt counter. So it doesn't go down unless you enter a correct password.
Okay. And I guess my question is like, why you said you needed to do that on the server side regardless of, because the client needs to tell whether it succeeded or not with the decryption, was that right? Yeah.
Sorry, can you restate?
Oh yeah, so you said that you couldn't put that at a later stage.
Oh, right, yeah.
Because of the client and so on. So couldn't you go around that by like deriving some signature key with that material? Or, well, sorry, I guess I'll take it offline. Yeah.
Okay, we need to move on to the next talk, so let's take the questions offline.
Right.
Thanks again.
Thank you.
And the next talk, Matilda Backendal and Miro Haller will talk about why end-to-end encryption cloud storage is hard, challenges, attacks, and best practices.
Yes, thank you. Okay, yeah, so welcome to this talk on why end-to-end encrypted cloud storage is hard. This is based on some observations that we made when studying the end-to-end encrypted cloud storage service Mega, a project which led to a paper titled Mega Malleable Encryption Goes Awry. And this is joint work together with my colleagues, Miro Haller and Kenny Patterson, and my name is Matilda. So let's talk about cloud storage. I'm sure you're all aware of the advantages of this service, which allows you to outsource the storage of your files to the cloud, such that they are available online, can be accessed from multiple devices, and provides you with a backup. Additionally, files stored in the cloud can be easily shared with other people, and many service providers even offer real-time collaborative editing. So for these reasons and more, cloud storage has become extremely popular. However, there is one major drawback, and that is the lack of privacy. So what do I mean by this? Well, when you choose to put your files in the cloud, they're no longer only on your device. Rather, they're first being transported across a network and then stored at the server. And neither of these two are entities that you necessarily trust. Luckily, we have secure channels such as TLS to protect the files while in transit, so here we're not concerned with a network adversary. Additionally, files are usually encrypted at rest in the cloud. However, and this is a crucial point, the most common approach here is to encrypt the files with a key known to the service provider. And this means that cloud storage implemented this way does not provide end-to-end encryption. Now, the most straightforward alternative approach to this is to instead encrypt the files with a key known only to the user. And this is known as client-side encryption. And when implemented correctly, it provides end-to-end encryption. So why do we care about end-to-end encryption in the cloud storage setting? Well, as we heard in the last talk, people want privacy. And why? Well, because without end-to-end encryption, the service provider has direct access to user data. And so, for example, they can read sensitive files or perform analytics in order to serve targeted advertisements. And even if the service provider doesn't do either of these things, there's always the risk that they would be compromised by some external adversary that wants to do these things or worse. Now, in contrast with end-to-end encryption, even a malicious or compromised cloud has no access to user data and cannot modify user files without it being detectable to the users. So we think that, well, ideally, end-to-end encrypted cloud storage would provide kind of a best of both worlds scenario in the sense that you get the features of outsourced storage with the security guarantees of local storage. Now, in order to achieve this, the system obviously has to provide data confidentiality and integrity, and this in a threat model where the cloud is potentially actively malicious or compromised. And in this threat model, there are some trivial attacks which a malicious cloud can perform and which we consider out of scope. So the first one is availability. A malicious cloud can always refuse a user access to their files. The second one is user anonymity. So this means we don't try to hide the mapping between a user's identity and their account, nor their access patterns. Third, a malicious cloud can always try to perform a targeted dictionary attack on user passwords. So as we saw in the previous talk, passwords are often used as the root of security in end-to-end encrypted cloud storages. And the only good way we really have of protecting against this is to enforce a strict password policy. Furthermore, there are also other ways in which a malicious cloud can try to extract user secrets. So for example, if you access your cloud storage over the browser, the server can serve you some malicious JavaScript code in order to try to get a hold of your password. And trying to integrity protect the JavaScript code is a very interesting problem, but it's not something that we consider here. So let's have a look at the state of consumer cloud storage today. This table shows the 4 biggest providers. We have Google Drive in the top with over 1 billion active users, OneDrive, iCloud, Dropbox, and so on. Now, surprisingly, or perhaps not, neither of these provide end-to-end encryption. So we might ask ourselves, why don't the big providers aim for end-to-end encryption? Well, it turns out that implementing client-side encryption is not as straightforward as it may seem, and rather it comes with some inherent challenges, and I'll try to illustrate a few of those for you here. So the first one is key management. Remember that we'd like to have the data be available from multiple devices. But now if the files are encrypted with a key that's not known to the storage provider, this means that this key needs to be available on all the devices where a user wants to decrypt their files. But without assuming an out-of-band channel between the devices, the only way we have of transferring a key from one device to the other is via the untrusted provider. So obviously this can't happen in the clear, so we need to encrypt the key in some way. But for this, we need a key encryption key. And now this key encryption key also needs to be available on all the devices. So we're sort of back at the start again with the same problem, and it's turtles all the way down. Luckily, if these devices belong to one and the same user, we actually have an out-of-band channel between them, namely the user themselves. So if the user can just remember the key and bring it with them, we have a solution to the key management problem. Unfortunately, users are not very good key managers. So it's inherently difficult for a human to remember a cryptographic key. So instead, the most common approach is to use a password as the root of security. And what this means is that a user-chosen passphrase is fed into some key derivation function in order to derive all of the cryptographic keys needed for the system. Unfortunately, users are not very good password managers either. So, and password management is really critical in the end-to-end encrypted setting, because if a user forgets their password, they lose access to all of their data. Additionally, passwords have a long history of challenges with low entropy and leaks. And if a password is leaked or compromised in this setting, well, it immediately leads to a key recovery attack, which undermines all of the security guarantees of the system. So in summary, we don't really have a good solution to the key management problem. And even if we imagine that we did have a solution in the single user case, for example, some smart way of using passwords, there's still the challenge of sharing encrypted files between users. Because if one user has encrypted a file and wants to share it with another user, they also need to share the key. Now again, the challenge is to establish a trusted channel between the users, where in this setting, the only point of contact that we can really reasonably assume is the untrusted provider. So these challenges and more is what we think makes implementing end-to-end encrypted cloud storage difficult and interesting.
So now that we have established that end-to-end encrypted cloud storage is desirable but not trivial to implement, we're going to look at how Mega, a specific cloud provider, tries to implement these challenges in their design. So who's Mega? They're the 5th biggest cloud storage provider. They have over 207 million users and store over 130 billion files. What makes them more interesting compared to their bigger competitors is that they advertise security and privacy. And they emphasize this on their website through statements like Mega does not have access to your password or your data. So in the following, we're going to have a look at the simplified version of Mega's design and see how they try to address the challenges of end-to-end encrypted cloud storage. So we're going to start with registering a new user. To register a new user, the user generates an RSA key pair that's used for authentication. It then uploads RSA public key to the server in plain text. It also picks a password and encrypts the RSA secret key with that password and uploads this to the server. The reason for doing this is that we want to be able to access this key material also from other devices. A registered user can then upload a file in the following way. It first authenticates to the server, and then for a new file, picks a key specifically for that file, encrypts the file with that file key, and uploads the encrypted file to the server. But the user also uses their password to encrypt the file key and then uploads this encrypted file key to the server. Again, the reason for doing this is that we want to be able to access this key material also from another device. And that works as follows. The user on this other device authenticates again to the server and then fetches the encrypted file. But it also fetches the encrypted file key and then uses their knowledge of the password to decrypt the file key and use that key to decrypt the file. So although the scheme that we described so far is pretty similar to the generic construction described by Matilda in the beginning, it already has subtle flaws on the implementation level. So next we're going to discuss cryptanalytic results from our paper Multiple Encryption Goes Awry that will be published in SMP this year. And in particular, we're going to start with an attack where the malicious cloud provider tries to recover a user's RSA secret key with an attack that's more sophisticated than just guessing the password. This attack is going to exploit the authentication protocol, so let's look at that in a bit more detail. First, the user sends an authentication request and fetches the encrypted RSA secret key from the server. The server picks a session ID and encrypts this session ID to the RSA public key of the user that tries to authenticate. The user then uses their knowledge of the password to decrypt the RSA secret key and uses that key to recover the session ID. And to conclude authentication, the user will send back the session ID to the server to prove that it successfully recovered access to the RSA key material. However, as the cryptographers in this room will probably have already spotted the big red flag that they're using AES-ECB to encrypt the RSA secret key. So some of you may now think of a Linux Penguin, which is the standard example of why not to use AES-ECB. If you encrypt the Penguin with ECB, you still have a Penguin just with a funky color scheme. However, it's actually not trivial to build a key recovery attack just from the fact that they're using AES-ECB. And the reason for this is that an RSA secret key is substantially different from a Penguin. If you want to encrypt an RSA secret key with AES-ECB, then you split it into different blocks and you encrypt those blocks separately with AES. However, the RSA secret key has high entropy, unlike the Penguin that repeats the same blocks of pixels over and over again. So really, for the RSA secret key, with very high probability, those blocks are different from each other. So just encrypting them, AES is still a pseudo-random permutation. So if you just encrypt them and you get some ciphertext blocks, you cannot go back to the plaintext blocks without breaking AES itself. So really, we are not exploiting that AES-ECB is deterministic in this case. However, what we can exploit is that those blocks are encrypted independent of each other. So a malicious cloud provider can garble one of the ciphertext blocks, and this will propagate and garble only one of the plaintext blocks. So the idea for our attack is that we garble part of the RSA secret key, then observe how the client uses this partially garbled key and learn something about the parts of the secret key that we did not garble. So we are exploiting that the cipher here is malleable. But how can we make observations on how the client uses this secret key? Well, if you go back to the authentication protocol, we realize that we have a partial decryption oracle because the server picks the ciphertext. And then if the client decrypts successfully, it will send back part of the plaintext in form of the session ID to the server. So putting this together to an attack, the server can exploit that RSA secret key ciphertext is malleable and change full AES-ECB blocks, ciphertext blocks, and then observe how the client uses this partially garbled key through the partial decryption oracle. And it turns out that if the server picks the right values for a session ID, this allows the malicious cloud provider to perform a binary search for the RSA secret key of a user. So the impact of this attack is that a malicious provider can recover a user's RSA secret key in 512 login attempts. This was later improved substantially to 6 logins and 2 logins. But if we take a step back and look at Mega's design, then we realize that every file is encrypted with its own key. And those keys are not encrypted with the RSA key material. So just knowing the RSA secret key does not allow an adversary to read a user's files. However, we were able to build a second attack that allows file decryption. So for this second attack, we're going to assume that the adversary already knows the RSA secret key from running our first attack. And the main observation for this attack is that in their design, Mega also uses AES ECB to encrypt the file keys. And they're even using the same key for this encryption. So essentially what we can do for our attack is we can pretend that the file key ciphertext is part of the RSA secret key ciphertext, and then cut and paste full AES ECB ciphertext blocks from the file key encryption into the RSA secret key encryption. And at that point, we can use the vulnerable authentication protocol that we already exploited in our first attack to learn the decryption of file keys. So the impact of this attack is that we have a cheap AES ECB decryption oracle that allows an adversary that already knows the RSA secret key to also recover file keys and therefore decrypt all user data. Summarizing our attacks on Mega and mistakes that should be avoided when designing end-to-end encrypted cloud storage, our first attack recovered the malleability of key material that's outsourced to a server to recover the RSA secret key of a user. And the problem here is that this key ciphertext has no integrity protection because Mega did not use authenticated encryption for this. Then we built a second attack on top of our first attack that allows the decryption of arbitrary AES ECB ciphertexts. And the problem here is that we can break the file encryption with a vulnerability in a completely separate part of their design, the authentication protocol, because they reused the same key for both of those parts. Furthermore, in our paper, we have 2 additional attacks that allow a malicious cloud provider to craft ciphertexts that decrypt to arbitrary files, even without the malicious provider knowing a user's password. And the problem here is that Mega designed their own file encryption scheme that has some non-standard structure that allows for these attacks. Finally, we also have an attack that's similar to the Bleichenbacher's RSA padding oracle, but adapted to Mega's custom padding scheme. And while this is another instance of homegrown crypto, it's also a legacy issue because Mega was aware that this part of their code is vulnerable. However, they were not able to move away from it for backwards compatibility reasons. But with that, we picked enough on Mega, and there's definitely things that they did do right. For a start, they aimed for end-to-end encryption, which is more than we can say of other cloud providers. Furthermore, they have a bug bounty program, and they were very collaborative during disclosure. In fact, we enjoyed this collaboration so much that we also decided to continue it and break their patches on our first attacks. But jokes aside, while working on their system, we realized that fundamental changes to their design are infeasible in practice. For instance, if you want to replace the file encryption, you need to re-encrypt all files, which would take more than half a year in their system. Furthermore, it's also unclear how you can recover from a compromise because there's no way to rotate keys in their system. So really, their design also doesn't offer post-compromise security.
So now that we've seen some of the issues that Mega faced, the natural next question to ask is how should we design end-to-end encrypted cloud storage? So summarizing some of our observations, ideally we think that a good, well-designed system should provide cryptographic agility such that it can recover from vulnerabilities, modularity such that it can be securely extended and to ease analysis. Of course, it also has to provide the basic features that make cloud storage so attractive, so multi-device access and file sharing, for example. But we might also want to aim for some more advanced cryptographic features, like the ability to recover from compromises or to protect your data from future compromise. However, achieving these things are challenging. So first of all, supporting multiple devices leads to a key management issue, and this means that users have to handle keys or passwords. Additionally, if we want to share files between users, we have to find a way to do a key exchange between them. And furthermore, achieving post-compromise and forward security is more challenging in the setting of end-to-end encrypted cloud storage than in, for example, messaging, because the data here is persistent. So Users want to be able to come back and access their files over and over again, which means that we cannot easily use ephemeral secrets to protect the files. And this makes achieving post-compromise and forward security more challenging. And these challenges, they stem at least in part from the fact that we're assuming a very strong threat model where we don't want to trust the storage provider for essentially anything beyond availability. However, somewhat paradoxically, we're trusting the providers today with the challenging task of designing the cryptography that's supposed to protect our data from them. And as we see in the case of Mega, this doesn't always work out. So what can we do about this? Well, we would like to propose a standardization effort where various stakeholders from academia and industry come together in order to design a well-analyzed and practical end-to-end encrypted cloud storage system that we can all trust. And with that, I want to end with a question for you, and that is, how can we interest providers in such a standardization effort? We don't have an answer to this. We're hoping that some economic incentives, like allowing customizable features or an integration into their ecosystems, can help, or perhaps political incentives like data privacy laws and regulations on the security that a system needs to provide. But we'd be super happy to hear your thoughts. So if you have any ideas, please come talk to us in the hallways. And with that, I'd like to thank you for your attention.
Thanks for the talk. Could it be possible to design a client that does all of the encryption and just treats a service provider, an existing service provider, as a black box, where you don't rely on anything from them other than them hosting some bits that you encrypted yourself? Wondering if you could pursue the standardization strictly by building a client-side app.
So I think the issue with this is the key management between different devices, because if you're only, as long as you're, basically this is like encrypted backup, you encrypt your files, you upload it somewhere, and you don't care what the other person is doing. But then how do you get the keys from your laptop to your mobile phone? I think this is where we sort of need to have some support from a cloud provider.
Two very related questions. So the first one, if you just replace encryption by authenticating encryption, don't do trivial things, do you believe that Mega system would be secure? And kind of related to this, do you have actually a model? I mean, I know it's an open question, but do you have a model of some things that you consider secure and maybe some secure solution?
So I wouldn't propose to use Mega's design, even if they were to change some of these things, for the reason that they don't provide most of these ideal features that we like. So they don't support things like key rotation, for example. There's definitely not cryptographically agile. It would be very hard to provably show that their system is secure. And yeah, it's work in progress to make a security model that we can use. Mm-hmm.
Hi, thanks for the great talk. So one desired property that I didn't see is that detecting when many users have the same file, like a book that thousands of people may have, because this can help storage provider to reduce their costs a lot. And have you thought about what is the impact of like this encryption on cost and scalability, and an extension of that, trying to improve this scheme in a way that you can detect whether a file is common in a privacy preserving manner, and do two-way of like handling privately created and more generic files separately?
So I think a fundamental issue is as soon as you are able to detect, like you need to have a deterministic encryption scheme to be able to detect that two files are the same if they're encrypted. And then you only have in CPA security instead of in CCA security. So there are definitely trade-offs between performance and security here.
No, and just to say, I mean, if someone like Mega wants to implement a system without deduplication, I think that's something we should applaud, right? Because it does give higher privacy guarantees for the users. So.
Let's thank the speakers. There is enough. And the last talk for this session. Luca Hirschi is going to talk about reversing, breaking, and fixing the French legislative election e-voting protocol.
Thank you. Can you hear me? Yeah. Okay, so my name is Luca Hirschi, and this is a joint work with Alexandre Deban from INRIA Nancy in France. And indeed, I'm going to tell you the story of how we reversed, broke, and fixed the French legislative election e-voting protocol. So, last year, they used a new protocol to organize the largest e-voting election ever, not only in France, but worldwide. And by largest, I really mean in terms of expressed votes, in terms of ballots that were cast. So more than 500 ballots were cast using this new protocol that we're going to call FLAP here in this talk. So that was a strong enough motivation for us to try to assess whether this protocol was secure or not. And we focused on two central security goals in e-voting. First, ballot privacy, which means that an attacker should not be able to learn how voters vote, obviously, but also verifiability, which means that voters must have somehow a guarantee that their vote has been counted and not tampered with or dropped. So let's talk about this protocol a bit. Here are all the agents involved in the protocol. So obviously you have a voter voting from a voting client, which is essentially a JavaScript program running in a browser. And it connects to a voting server hosted by the French ministry here. And you also have decryption trustees here, who each of the officials has a key share, and together they will be able to decrypt ballots. And finally, you've got third party here, run by independent researchers. And those will observe the election, do some checks to make sure everything happens as expected and that there was no attack that could be detected. So next, we wanted to know how the different agents interact with each other, what crypto they use, what kind of checks they do, and what kind of messages they exchange. But sadly, at the time, there was no comprehensive documentation or specification of the protocol. So we had to do it ourselves. So we looked at the voting client, we looked at mostly the JavaScript program, but it was obfuscated. So we had to reverse it. And so we did so that today I can tell you a bit more about the protocol. I will give you really an overview of the protocol, a very high level view, but all the gory details are in the paper. So first the voter picks a choice, let's call it V, and the voting client is going to asymmetrically encrypt it with the decryption trustees key. And it also computes some zero-knowledge proofs to prove that this is a valid choice. It's an encryption of a valid choice. And it also binds this to some metadata of the election. And this is how ballot privacy is supposed to be satisfied, thanks to this encryption here. Okay, then the voting server is going to compute some receipt for this ballot. Essentially, it's a hash over the ballot and some metadata, and also a signature over this hash. And in the metadata, there is the ballot box identifier. This is important because for that election, there were many ballot boxes, one for each consular, which corresponds to a city. So for example, there was a ballot box for Sydney, one for Atlanta, let's say. And this is important because the results will be published per ballot box. So we're going to have the results for Atlanta and the results for Sydney. This is then displayed to the voter on the voting client, and you can even download a PDF file containing those receipts for later use. And then the voting server is going to store all those ballots, put them in the corresponding ballot box, and the decryption trustees are going to decrypt each of the ballots, each of the ballot box, and publish the results per ballot box, as I said. They also compute some zero-knowledge proofs proving that this decryption is correct, and all of that is checked, observed, and checked by the third party. Also, the voter can use the receipt it got to ask the third party whether their ballots were really counted or not, because from the receipt, the third party can identify the corresponding ballot and make sure that it was indeed in the ballot box that was used to announce the result. This is how verifiability is supposed to be achieved, through those receipts. Okay, so I've already mentioned the two central goals we're going to analyze here, but when do we expect them to hold? So here are the different agents. I just added here the communication channel agents somehow. You can think of this as, so you can think of a compromise of the communication channel as a weaker attacker than the voting server attacker, because here we just assume that somehow the attacker is able to decrypt TLS packets and modify them, possibly. For example, if the attacker has a certificate of the voting server, that's one example. It's a strictly weaker threat model than assuming a compromised voting server. Okay, so when do we expect the properties to hold? This is kind of the standard for state-of-the-art protocols in e-voting. For ballot privacy, you can have the property under a compromised voting server and also a compromised communication channel. And for verifiability, you don't even need to trace the decryption trusses. And as we shall see, we found attacks on the FLEP protocol on an even weaker threat model. So when the communication channel is compromised, or if you want, when the voting server is compromised as well. Okay, so let's summarize a bit the different things we've done around this protocol. So thanks to the reverse, first we were able to provide this comprehensive specification of the protocol. So that was the first time we provided such a public document. And based on this understanding, we found two vulnerabilities on the system on which we base 6 different attacks on verifiability and privacy. And so in a responsible disclosure with the vendor and the ministry, we proposed different fixes, 6 of them, and most of them are already implemented for the next election that are going to be organized in a few months now. And from this analysis, we draw lessons for like any system, any deployment of such a system. And I will briefly mention some of them at the end of the talk. Okay, so now let's dive into the attacks and the fixes. And let's start with the attack on verifiability. So here is the flow of the protocol, the overview of the protocol I just shown you before. And here we are going to assume a compromised voting server. The rest, the other agents are supposed to be trustworthy. Okay, so what the attacker can do here. So when the voting client sends a ballot associated to the voter's choice, the voting server should compute the receipt, right? And this receipt must match the ballot that has been computed by the voting client, right? Indeed, there is such a check in the JavaScript program to make sure the receipt matches. But to be honest, it's quite of a mess because there are at least 4 different receipts handled by the voting client, 4 of them. And there are many different constancy checks, but they're flawed because in that mess, we found a way for a malicious voting server to provide attacker-controlled receipt that is going to be displayed to the voter. And the voting client is not complaining, it will just proceed and show this fake receipt to the voter. So what does that mean? It means that then the voter will use this fake receipt to check verifiability, right? And because it's attacker controlled, it really means the voting server can tamper with the ballot, compute a ballot for a choice of, for a vote of his choice, compute a fake receipt accordingly associated to this fake ballot, and the voter will use it to ask the third party, hey, is my ballot counted? And no, not your ballot is counted, but the fake ballot associated to the receipt you provided me. So neither the voter nor the third party is able to detect such an attack. So what's the impact? The impact is that for a voting server attacker, and we show in the paper also for a channel attacker, the attacker can stealthily modify the outcome of the election by modifying ballots or dropping ballots, as we show in the paper. That's pretty bad, because that's what we ask from verifiability. But that's not the end of the story, because we also found issues regarding privacy. So the main problem is at the design level. We found out that the ballot zero knowledge proofs do not bind the ballot box identifier. So it's not in the metadata in the proofs. But fortunately, it's in the receipt, in the hash. The hash hashes the ballot and some metadata. But that's not sufficient, as we shall see. This is the attack I will describe now. So assume a voter eligible to vote in Sydney. So he will pick a choice, compute a ballot, and the voting server keeps this ballot as is, but it will store it in the wrong ballot box. Here, for example, the one for Minsk. And it will compute a receipt for this ballot, but for the wrong ballot box, here Minsk. And at the end, the voter will use this receipt, and the third party will say, yeah, your ballot has been counted, but in the wrong ballot box, but no one is able to detect this problem here again. Note that if the ballot box was in the zero knowledge proof metadata, then this would not be possible, because the third party would say, no, your ballot is counted, but in the wrong ballot box. So this is a problem in itself, but why does it impact privacy? It does because of this attack I will present now. So here we have a target voter eligible to vote in Sydney, and we have a compromised voting server. What can this server do now? It will do the following. When the voter casts a ballot, so a ballot, voting for an unknown vote option, so here V question mark, the voting server will not store it in Sydney, but in Minsk. He could choose any ballot box, and here we just assume he will choose a ballot box for which there are a few expected voters who will actually cast a ballot in there. Maybe Minsk, I don't know. Okay, so the voting server will compute the fake receipt as I explained. And when truly eligible voters for Minsk will cast a ballot, the voting server will apply the previous attack to modify to compute a new ballot for an option he knows, for example, V1. Okay, and for the second one, maybe V2. And at the end, this ballot box will be decrypted by the decryption trustees that are assumed to be honest, right? So they will do it, and they will publicly announce the result for this ballot box. And because it's public, the attacker knows it as well, right? So he will know that V1, V2, and V question mark was in the ballot box. And because he knows all the votes except V question mark, he can infer V question mark and break privacy. So again, for a server attacker, and also for actually a communication channel attacker, it is possible to stealthily learn some target voters' vote. And also we show in the paper that you can do that on a group of voters, and this way you can exercise some coercive power on those voters, just to make sure, to prove them that, yeah, I will be able to know if you voted as I instructed, so that you can exercise some coercion. Okay, so we found those attacks, we disclosed them to the vendor and the ministry, but we also wanted to propose fixes, right, to actually fix the system. And we proposed 6 of them, and I will briefly mention 3 of them here. So first, obviously, you want the voting client to display the receipt as at least the hash as computed by the voting client. You can do extra checks if you want, but the hash that will be displayed should be the one computed by the voting client, the true one. This has been partially done for the next election already. So I won't go into the details of why partially, but yeah, okay. There is a way for a cautious voter to now detect this attack. It's not ideal, but at least there is a way. Second, we want the ballot box identifier to be bound by the zero knowledge proofs. This is done now and will be used as is for the next election, so it's fixed. And we also want a third party to actually check that those ballot box identifiers are consistent now. And again, this will be the case for the next election coming in a few months. yeah, so all of that thanks to this responsible disclosure, and also special thanks to the ANSSI, which is a French agency who was really proactive in this process. Okay, so in the remaining time I have, I will try to draw some lessons we can learn from this experience, this analysis. So first, I have to say, and maybe that's surprising, but I will explain. I have to say that this FLEP protocol was based on or inspired by a state-of-the-art academic protocol called BELENIUS. And this BELENIUS protocol is proven secure, was proven secure, both for privacy and verifiability. And the vendor had to adapt it for this real-world use case for the previous election. And it has to re-implement this protocol, deploy, do some audits, right? And you end up with this system used last year, which is badly broken, which was badly broken with those attacks. And I mean, other concerns we describe in the paper, but that I have not talked about today. So how come you start from this very secure protocol and you end up with this badly broken system? And what can we learn from this? So first, you could wonder why they had to adapt the design. And I would say this is mostly because state-of-the-art academic solutions, they lack features for real-world use cases. Typically, I mean, just two examples. First one, they cannot handle multi-ballot boxes. And this is crucial to be able to actually announce fine-grained results per ballot box. And so it's not only at the design level, it's also for stating the security properties, especially privacy, and in the proofs, in the security proofs. This is just not described at all. Also, they had to have downloadable receipts, so those PDF files. This is an extra problem because then you may want to generate them at the server and not the client. So then how do you check that they're consistent? This is another issue they had. Also, currently there is no practical solution to really distribute trust for authenticating the voters. So right now it's a single point of trust. And you have to trust one entity for eligibility verification. That's pretty bad, but there is no practical solution to date. And finally, for this design level, sometimes you have a trade-off to do between enforcing your properties at the protocol level, so mathematically in the crypto, or through operational rules. And obviously, I mean, it's much better to do it mathematically, but sometimes you have to do a trade-off here. And for example, there are rules under which you can decrypt, rules for the core ROM that can decrypt a ballot box. There are legal rules, and not all of them are enforced cryptographically, but only as operational rules. But that's also because there is no academic solution for this. So that's another open problem to look at. And finally, you have to implement, right? Deploy, audit such a system. And here they made this mistake with the receipt in the code, which is inexistent in BELENIUS, in the first system. And maybe that's, and despite the audits, right? And maybe that's because the focus of those audits were more on the server. They want to secure the server. But for e-voting, e-voting is radically different. You don't really care about the voting server. It can be compromised, can be flawed. You don't care because you have verifiability. What you care really about is the voting client. It's actually the critical component. So you have to make it trustworthy. So I think you have to open the spec and the code, at least for the voting client, and obviously audit this system. You also have to make it monitorable, which means you should be able live to detect if there are differences between the voting client served at your system versus the true legitimate one. And also you have to simplify and, I mean, first specify and also simplify the voters' tasks, what you expect from the voters, and assume no more, because they won't do extra checks if they don't know. And I mean, on a more general note, I think it's important for such a critical system to promote transparency and openness with first clear security objectives and threat models. This was not the case for that system. Ideally open specification, maybe even open code, FLOSS, and also promote public scrutiny, for example, through bug bounty programs. And they do that in Switzerland, so I think that's a good example. So I think I will stop here, thank you, and I will be happy to take your questions now.
I'm sorry, but we are really out of time, and we will move the questions to offline. Okay. Thank you very much to all the speakers and to everyone attended here. And